In this video, we are going to talk about maybe new, future, or one of the possible techniques how to design schematic and PCB. And it's very unusual because what we will be doing, we will be writing code and we will be specifying what we would like to design. And basically, I don't know exactly how these connections are going to appear, but Duncan is going to explain all this. So what exactly we are going to talk about today?
Yeah, so today I'm going to go through how do you write code to design circuit boards and try to show useful things to answer the question, why would you write code to design circuit boards? So I'll start with a fresh project and show like, all right, from scratch, here's you write simple code, and here's how you export it to Altium. I'll go into a tutorial for probably a regulator next, just to show like how do you get programmatic reuse out of your code. So how do you make a parametric power regulator? Then we'll go, so Robert, you mentioned you were working on a keyboard, and I built a little importer to make mechanical keyboards. So maybe we can make a custom one on the fly just by importing a file. And then we can look at a more typical design, which is there's this little IoT device, power efficient, highly integrated SoC with some flash memory. And can you use this new type of auto router to do it on 4 layers instead of the reference design, which is 8? And then finally, we can get into how do you do constraints for more complex interfaces. So this one's DDR3, which I think is a bit more complex than DDR4 and 5. It just gets faster, but it gets point to point. So DDR3 has got some interesting pieces to it.
Okay, so I think first what maybe we would like to talk about is why to write code, what kind of advantages we could get instead of drawing everything manually.
Yeah, I think that's a really important question. So the reason to write code is because it is a faster and more correct way to design a lot of things.
I'm sure now many people will be like, no, that's not true. Like, you're a software engineer, maybe for you, but I'm hardware design engineer. I really like to draw the schematic and draw the tracks. So you need to be more convincing. Why?
Yeah. So
I think you mentioned.
And to be clear, I'm a hardware engineer too. I'm not a software developer. My coding skills not very high. And for sure, some people like went into electrical engineering so they would never ever have to write a line of code. They're just like never. And this is like not going to be a tool for them. It does let you draw tracks and things, but if you don't like writing code, you probably don't want a code-driven interface. But some electrical engineers, especially those who have touched an FPGA or written some firmware, written some Python or some MATLAB.
I like to write code, actually. So I really would like to see what will be the benefit. I know you mentioned one of the benefits is, for example, schematic will kind of be created in real time based on the position of the component, for example. So you specify like what kind of pins can be swapped together, and then when you move it in PCB, automatically schematic is adjusted based on all these possibilities. Or am I wrong?
Yeah, that's right. No, that's right. So here, starting with the most advanced example before we go like building basic blocks, this code sets up the connections between a bank of memories and the memory controller on this IMX6. There's some key things here. So this is a require statement. So this says, I need a DDR3 16-bit data lane. Actually, I need 4 of them from the processor. I do not have to specify the pins. Right?
So this is how you draw schematic, basically. We are now drawing the schematic.
Yeah, draw schematic. I think the code model is, so instead of, you have a usual flow, which is you kind of sketch out requirements and you Google for parts and you read PDFs and you build some spreadsheets and then you do all your design somewhere, and then you start drawing it in the capture tool, right? And then you go from your capture tool to your layout, and you kind of like moosh around through this process between like a lot of your design work, which is not actually in your schematic. It might be in there as notes, right? Or for you, it might be in there as videos of like, all right, here's how you swizzle the bits in the data lane, right? but it's not in your tool. So the code model is write code to go from requirements all the way through to the factory, take all of the usual separate manual steps and just like put them in code and run it all at the same time. So when you run your code, you're doing your schematic, you're doing your layout, you're doing your analysis and verification. And that just happens every time you run your code. So you kind of always know where you're at. It's not going to be fully done to start with, but you can sort of build it out over time. So think of code as like requirements through factory, and anything in there is fair game. And it's about how do you write code productively to like just automate that? Because the advantage should be like it's much faster and you have a lower chance of making mistakes. Like for the product, what we shoot for is like the fastest way to get a working board on your desk. You can't just go fast, because if it doesn't work, you've wasted a month, right? So it has to be both fast and correct. And that's what we should get out of code.
So I would like to,
Yeah.
so if I understand right, so you basically write the requirements and everything else is kind of automatic. So you can actually minimize mistakes which you may do when you are, I don't know, drawing the connections or something. So this is something what you don't have to do. You just specify, I would like to connect this to this.
Yep.
You need to be sure this specification is correct, and then everything else is somehow automated.
Yeah, that's right.
Okay.
And instead of that somehow automated thing being a black box, it's all just like open source code. Like you can get in there and look at every single piece all the way down. There's no black boxes here.
Okay, so let's have a closer
So in this
look.
case,
Yeah, I'm curious. Yeah.
Yeah, you want to dig into DDR. All right, let's do the most complicated thing first. All right, I'm going to turn off the rat's nest so you can kind of see a bit more clearly what we're looking at. So we've got our chips and our memory controller. Let's see, if I pick a thing on ground, I can say A, and it'll highlight, all right, here are all of the ground pins. And then I could do something systematic with them, like, I don't know. Here, I'll break those out. If I pick a DQ pin, for example, I can press Control A and see these are all of the possible sites for this DQ pin. So the full memory controller from the processor is modeled in code. It knows about all of the bit swappability constraints. So I haven't routed anything, because what I'm going to do is like, I'm going to build my schematic with the router. Because the usual flow here is be like, oh, I'm going to kind of like draw traces in from both sides. I'm going to read the data sheet, and I'm going to edit my schematic, and then I'm going to like connect them, right? So instead of that, you can just say, all right, I want to pick a pin here, and maybe I'll pick one explicitly. All right, so now I've made a trace. That makes a connection. And if I pick another data bit in this lane, you can see that the selection
This
field
is cool.
is
So
greatly
basically
narrowed.
what happened when you were connecting the very first pin, you could connect it to all the banks and all the data signal. But once you connected this specific signal from this bank to a bank in processor, then the next data signal from same bank only can be connected to this bank which was already connected.
That's right.
Wow.
Because that's the truth of your design.
Yeah, cool.
Right.
This is really cool. So before we continue, I'm curious, how did you specify this? So in the code, can we have a look?
Yeah. So this is what the
closer
code looks like. So this would be code that you run inside your processor module. So we have modules, which is, think of it as a subcircuit, and you put other subcircuits in your subcircuits. So you can just make this hierarchical composition of things like this. So these are those required statements. So this, we do a lot of importing when we write code. So the processor typically has some, let's see here, where's our processor? It's going to be this big thing. So there's a lot of auto-generated code here, including, here's like the very detailed model for, okay, this processor only made available just the names of the signals. So how do you parse those into the structure of DDR lanes, right? So that's all the stuff under the hood. A lot of this stuff you just get to reuse. So, so like most DDR banks, you can just write a single function, set it up systematically. And then it's also adding all of the topology, impedance, and timing constraints in the same function, right? So in your code is a model of your stack up and your materials and your routing structures. And that will tell you, let's see, can I go to this? All right, here's an 80 ohm differential routing structure. So it gives you the dimensions and it's per layer. You also have a propagation velocity, right? You also have an insertion loss per millimeter. So it's using those to be able to do things like length matching, make sure you're meeting your loss budget. Not showing up right now because it's saying like, hey, these things aren't routed and I don't know how to satisfy those constraints. Yeah, okay, so it generated 796 constraints for your DDR3 bus, which is, length matching, like all of that, right? So that's the model. You try to put the truth of your design in code so it's systematic, and then when you run it, it just makes designs. Okay. And we built a lot of solvers so that writing code just becomes really productive, like this auto router, like the pin assignment, like supply chain integrations or Altium exporters, to just make the code more useful as a way to design things.
So first, I can imagine one of the advantages is probably you can reuse a lot of stuff in next designs. Or if you need to modify your existing board, I guess it's going to be like super easy because you already have almost everything. But even if you have normal schematic, it's easy because you don't have to redo everything. But I would move back to maybe something more simple.
Oh, yeah, you don't want to start with DDR? Okay.
Yeah, because maybe this is too complex. But this is to just show what are the possibilities. But let's have a look on something very simple. Let's start something from scratch to understand a little bit better, like how this simple circuit can be created.
Right. Okay, yeah, let's start from scratch.
I'm curious.
Yeah, all right. So this is the JITX tool. We launch inside VS Code, which is just like a cross-platform programming tool. So yeah, I'll start new project, put it there, call it from scratch. Okay, so when you make a new project, it sets up, so we have a common library that we ship full of like circuit utilities like, I want to generate box symbols from importing a bump map. So just a bunch of like useful little software tools like that. And some example code to get started. So to create the design, I run this code. So if you look at what all this is doing, it's importing things. You set up your board shape, and everything is code. Like all your components are code, all your symbols are code, all your land patterns are code, and your boards are code. Then we have a sub-circuit definition here. So this is a PCB module, my design. I create some ports. So if you want to attach to the sub-circuit somewhere else, this is how you kind of expose the public interface of a circuit. And then there's two things. So I have this convenience function to add a resistor between those two ports. And that's a 10K resistor. And I also place a silkscreen label that's parametric. And that's it. So when I run the design, it's also choosing a stack up, and that stack up has materials. You set your schematic paper size and all that.
Okay, so this is basically just a resistor and maybe like...
Just a resistor, yeah. So our schematic is not very interesting. It's a resistor. Our board is a resistor.
Wait. So how did you create... So this is basically, once you write the code, you can see the schematic?
Yeah, exactly. Once you run the code, it creates your design. So I could say, I want another resistor. Okay. Sorry, I'm using a Windows. Sorry, it's tough. I'm using a remote desktop connection to Windows through a Mac, so my keyboard is a little weird. That's all right. So now we should have two resistors. And the model is, you write code, you run it, and then you have your design.
Where are two resistors?
There's two resistors.
Any schematic?
Yeah, schematic needs to update. All right, I am on a bit of a development build here. So I bet I could get it if I wrote. Yeah, there's my two resistors. Okay, so I just needed to push an update. And that's it. So they're attached between the same signals. And then the schematic hey, if you like dragging things around, you can still drag things around. So this is to get your aesthetics tuned up to be, this is how I like to lay things out.
And how did you connect the layout? I didn't see it because initially there were only resistors, correct?
Yeah, and there's still only resistors here. This is a convenience function that, let me just do the raw thing. So a common thing is you say instantiate, which means like add a thing. We'll call it R, and it's going to be a chip resistor.
Okay.
What's your favorite resistance? Do you like
10K?
10K?
Yeah,
10K. All right. So I'm just going to pass it a single function, which is 10K, and I'll add 2 of them. All right. So I run that code, and I should have 2 disconnected resistors, basically. So yeah, that's disconnected, and then schematic. It's a little slower to update.
Okay, schematic will update it. Okay, so you have 2 resistors in your board. Okay, and now how do you connect them?
So they have pins, P1 and P2. So then I would add a new statement, say net R, and it's an array. So I'll pick the first one, P1, and R of 1, P2. So this will...
So this will connect the 2 pins.
Yeah, this will connect them end to end. So you should get 1 single net here.
So, but they are, right now they are still not connected. This is just the visual.
Yeah, this is just the net list.
Okay.
Yeah, and then we built an auto router to connect them.
What did you do?
Oh, I just pressed route. So we have a new type of router in here. So it's an auto router, in that you're not going to draw the exact path. Well, you can draw the exact path. But the way it works is you select a layer and a set of pins, and then it will route them.
Okay.
So like this, and I just press Q, which is route, and now I have a trace. And this trace is following all the rules of my stack up. I can't really get it to bend around interesting things here.
How can you make it
yeah, there it goes.
Wider, for example?
Yeah, you want a thicker one?
Yeah.
So then you can do it in code, obviously, but you can also get in there and edit it. So thick trace.
So
if it doesn't fit in the pad, so if it doesn't fit in the pad, it will make an adaptive shape. So I made that significantly larger than the pad. So if I make that down to 0.2, it fits. So that unusual shape is really nice for power routing, as well as like sort of if you have like sensitive RF structures, you can do like very nicely tapered shapes pretty easily.
So when you have like some power pins connected together, then basically the auto router will create power planes automatically, not the...
Exactly. Yeah, and this plane is just a trace. So that here I set it to be adaptive, and it'll take that shape. And yeah, you get to move your layout around, which is nice. And your traces don't, they all update.
I see schematic has been updated.
Yes, schematic is updated. There we go. All right, so they're connected there.
This is interesting. We didn't draw the schematic, and it just...
Yeah, but it's still nice to have a schematic. Like a lot of people really like it when you're working with code. Like, I'm a very visual person myself. So this is my common mode of working. I'll edit the code, and then I'll see the schematic in the board updating. And so I'm still working with the views that I'm used to, but I'm driving it all from code, because you can't like draw something wrong and make an incorrect net. So you get all the correctness from code, but you still have that visual.
I would like, I always would like to have the schematic visible, because I think it's like super hard to imagine the schematic directly from the code in your head.
Yeah, no, I can't do that. I'm sure someone can, but it's not me. Yeah, so now...
Okay, so what I'm thinking about now is how good is the auto router? Because... I
look at it, it's great.
Because basically you didn't draw anything, you left it on auto router, and but I think you can draw it. If you want, you can draw it, correct? That's what you mentioned.
Yeah, that's right. I feel like I should get something bigger in here as a better obstacle.
Okay.
So I'm going to connect the other ends of these resistors just to have more nets to work with. And maybe I'll instantiate another thing. Yeah, why not? Just give it a pin header. Yeah, 5 pins. So, Windows. All right, so now we got more stuff going on.
Okay.
So yeah, we got our, I guess I haven't attached that connector to anything. But yeah, so the router itself can do a lot. So if I route these things, I rotate, it's going to continue to find paths for these things. And the nice thing is that all of these will respect your manufacturing rules and your SI constraints, as well as your power. So you cannot make like an illegal trace. You cannot make a non-manufacturable thing or something that does not explicitly follow your rules unless you like actively try to break them.
This can be sometimes tricky because I know, for example, when I'm doing layout, very often I actually break many rules, or just to be able to connect everything, then or see where is the space or something, and then I will kind of reroute it or fix it later. Because when I remember when I was trying AutoRouter, one of the biggest problems with this setup, you set up all the rules, but basically you end up with a design which was not able to route at the rules what you specified. So how do you handle this?
So
you can change the rules, make them minimal, I guess.
Yeah, exactly. Like you can change it on the fly if you wanted to. Right? I guess that changed the clearance. But from the product point of view, you make that an active thing you have to do. Right? So by default, it's going to be creating correct geometry, and you can have it. You don't have to load the rules in. You can add them in later and then inflate the traces. And I think you can do things like, let's see, make some gratuitous differential pairs if you wanted to. Let's see here.
When we are doing, oh wow, can you place it on the other side of the board? I'm curious what will happen.
Oh sure, yeah. So
no, only one of them. Only one of them. I'm curious.
Oh, just one of them. Oh, okay. Yeah. So I did that. So I flipped this to the other side of the board. I'd probably get some vias out. So another thing you do is there's automated via tools to just automatically fan out. And then here I would be what, 3 like that, like that. And then I think one nice thing is that the differential pairs have the same. Of course, I break it right away. Oh, I know what's going on. Hang on. So the model here is you select. It's very fan out based. So let's see here.
So you do some kind of fan out from the because it's differential pair.
Yeah. So the model is you fan out to your insertion point here. Just become a little hard to touch. There it is. And then your fan out moves with your components, so that the pair will adapt as you move it, which is nice. So like this is what it means to this is what I mean by it following the rules and trying to find a path, right? And then you could get in there and you could break it, right? But I found I'm really pushing the auto router and trying to do things in like many fewer layers than is usually possible. And you find that you don't need to break the rules so much. You definitely can, right? And it's fun, but I don't know.
I would like to point out this what we are showing. It may look like super simple design, but I know actually your tool is aimed for like very high speed design. So I would like to point this out because some people may think it's for playing. It's not for playing. So tell a little bit more about what is the target? It's like, is it like
Sure.
hobby designs and ESP32, or is like server boards, or?
Yeah, that's a good question. I do enjoy playing with it. You know, I do my own personal projects. But yeah, our customers they want help with their complex designs. Very few people are like, oh, I'm going to choose a new tool to learn to help me with my easiest designs. This is not something that people really do. So this autorouter, for example, you notice it's curvilinear, right? Everything's curved by default. And you've also given up some control, like you're not clicking out the exact path. And the reason to do that is because we can then put perfected signal integrity geometry directly down on your board without you having to do it manually. And this is really helpful for next kind of higher frequency interfaces like PCIe 5, 30 gigahertz now. You have to make sure that, I think over the span of 20 millimeters per route, you can't build up more than 1 picosecond of skew in your differential pair. So you have to like do this instantaneous deskewing, which we can do automatically because we know what it's for, and you've given up the control so that it will be able to do that. But that kind of thing is really hard to do in existing tools. Even just any angle differential pair routing is kind of tough. So yeah, our customers are generating like, 60, 80 page schematics. It's doing things computational. Yeah, there's some really big designs out there. Doing things computationally is like, turns out to be a great way to handle complexity, because your design, you can think of it kind of locally at each level, and then computers are just really good at handling large numbers of things.
Now I'm thinking like why I heard about your company, of course, because we have been in contact for a couple of months, but before I never heard about what you are actually doing. So let's talk a little bit about your company and about your product. And I don't want people to think like this is an advertisement. We are not making this video as an advertisement. I just find this very fascinating, like creating schematic and PCB through code, because I remember the times when I was, drawing some complex designs, and I was like, if this would be in code, it would be so much easier, because I finish schematic, and then when I have to do checking, and the checking can be very easily specified in software, like connect this input to this output, and doing all this checking manually, it's time consuming and you can make mistakes. So that's why I find this fascinating, like just specify your components and connections in code and let it go, and everything will be checked automatically. That's why I find this fascinating, and that's why I also suggested to create this video, because I think some people may find it really interesting that there is this kind of way actually to create designs.
Yeah, well, thank you.
So let's go. Let's talk a little bit about your company.
I'll show one more thing first.
Okay.
Before we leave Windows behind, is that, let's see here. I think we got Altium background somewhere.
Oh, you can import this to Altium. I think that's what you mentioned. Oh,
that's right. Yeah. So at the end of the day, if you want to do something in Altium, it's already done. Let me find it. I think it's that one. Is that my design? Yeah, there's our. Oh, that's an old version of it. But yeah, and that's the idea, is that anything you do can be exported to Altium.
Can you do it with the current design? I'm just curious, because now.
Yeah, let me see.
So everyone see.
Get that board saved. Yeah. Run that one more time.
Oh, you didn't save it. That's why it was the old design.
Yeah, I think I ran the old one. I don't need to save it. It's a generated project. So yeah, it'll write out basically a native Altium CAD package. We're officially partnered with Altium for this. Yeah, there it is. For this integration.
I've seen it there. It was there.
Yeah, it's in there. There it is. Differential pair. Of course, I don't think Altium Yeah, it's not so great with curves, and they can't quite dance like we can. But you know, it's there. It's native.
And schematic, show me schematic.
Schematic, yeah. And yeah, so this is like a fully linked, correct CAD package with all of the native CAD parts. So you can get in there. You could, you know, if you want to start drawing things, you know, you could, if you wanted to.
Okay, okay. So now let's go back to your website.
Yeah. All right. So so here's a website, which I will say is pretty out of date with this demo, but the product I'm using is released. So I got to make new videos. Maybe I'll record them after this to replace the front matter.
Okay, so your company is called
JITX.
JITX. Okay.
Yeah, stands for just in time everything.
Okay. Pricing. I see pricing. Show me pricing. I'm curious.
Pricing. So there's
$1,000 a month.
Yeah, for a small business, it's definitely expensive in terms of a tool. Pretty cheap in terms of your time. We also have, especially for smaller teams, there is a. Oh wow, it's not showing here. We have a token program, so you can actually get daily tokens.
I see.
And when you buy those up front, you get like a discount.
So how do you use tokens?
It's just a daily use. So if a lot of smaller design teams have kind of spiky usage of their tools, right? So a monthly subscription doesn't make sense if you don't have that much design work. So then you can just use a daily token.
Okay, so it's $60 per day.
Yeah.
Okay.
Or $30 per day when you buy your first set.
Okay, and I've seen you have also something free for education and for open source.
Yeah, that's right.
Okay.
So we have a program. You know, I started JITX because I was a grad student roboticist at Berkeley, and I was designing all of my own robots from scratch. And I got so fed up with design tools that I decided to kind of build a better one. So we definitely want to support. I think there's a generation of engineers to get into design. A lot of them are leaving for computer science right now when I talk to people out here. So yeah, we definitely want to support our educational users. And we also have an application for open source development. So if you do a lot of open source contributions, we're making things like a package manager, for example. So you can like share your code, because right now you can open source a hardware design. But if someone wanted to like change it, they would basically have to be able to like run the full analysis and like almost be able to redesign it from scratch. And that's not the same thing you get with open source software, right? Because open source software, I can upload a script and like 50,000 people can use it in their projects, right? So we can do that for hardware. And so this open source aspect is something I'm excited about as well.
So basically, once you share your code, then people can very easily modify PCB or schematic or something, and it's what you just showed. It's
you could write a library saying like, you know what, I really know how to design transimpedance amplifiers really well. And you can just make that into a software library such that anytime someone designs a transimpedance amplifier, they can use your expertise. How do you choose parts? How do you constrain the design? What's important about it, right? And then you can do all of design that way. And so that reuse gets a lot more meaningful, because you could upload, like, here's a transimpedance amplifier schematic, but you only get one. But when you write it as code, you can do like 50% of them, 80% of them with like a single library.
I'm just thinking, like, even the memory example what we had, theoretically, someone who understands how to design memories can write the code, like including the pin swapping and everything. And someone who never designed memory before will be able to use this model or this code, even if they don't understand like how to do pin swapping, because it's already done. They can just maybe modify shape of the board, fit the or adjust the placement or something. I don't know. And oh, okay. Okay, now.
And I think the router serves that goal as well, because you can load all the rules into it. And then it's point-to-point clicking that follows your signal integrity architecture. So even someone with less layout experience can now do a pretty high-spec design, even if it's their first one, which is what our customers are seeing. Because like they have typically very senior engineers and then very junior engineers. So how do you get these people up and productive quickly? Code can be a way to do that.
So how to justify this $1,000 a month? What are the other advantages? You say
So
speed. How you how you speed up your process by using this?
Yeah. So justifying the price, it is the customers measure it against the contractor time that they're saving or the time of their own engineers, as well as the reducing the risk of hardware development. So you can like greatly increase your chances of first pass success without spending 2 months in review. Because some design teams will say like, we never make a mistake because we put it in review for 2 months and we'll just wait. But you actually don't have to make that compromise anymore. You can just like move faster and have a lower chance of mistakes. So that's hardware and time cost. Really trying to, this seems expensive to some people. For some people, it's just like, absolutely. Like this is like, what, 2 days of contractor time for me per month. If I can save that, that is already ROI positive.
Yeah,
and
I think if you know how to use it, maybe it can really save your time. But I would like to know how good it is. So I think we should go back. We should go back to.
Yeah, let's do some designs.
Yeah.
Yeah. Right. So maybe we'll come back to DDR3 later. Yeah, let me start with a sort of simple reuse design here.
Okay.
So, like before, we have our module, added a pin header, made some nets, VN ground, and set a ground symbol here. So that's going to make a, let's see here, is our schematic. Yep, a couple nets connected to ground. So where you start seeing the benefits of code is design reuse.
Okay.
So I think in a lot of tools you can make, some people will copy paste schematic sheets and then like edit net names to get them to line up and try to reuse that way. And I think some things you can do like reuse a layout across different groups. You can do the same thing with code, but a big difference is that you can make those blocks parametric. So here I've got a power regulator, and I'm saying I want the output voltage to be 3.3, my input voltage is 20, output current 750 milliamps, and I want a 60 millivolts ripple on the output, and I will say that I want it to be pre-placed. And now when I run this code, it is doing a lot of work because it's designing.
I'm curious.
Yeah, so what it's doing here is designing the feedback network for this part. So that's a voltage divider that under all variations of operating temperature, including the TCR, as well as manufacturing tolerance, the combination of these two resistors will produce the correct feedback voltage. And then it also makes sure that each resistor value is triply sourceable. Right? Because like you don't want to choose the like, all right, I've designed my feedback network using this like $9 resistor. You want it to be, and this was designed for, I think it was how do you design a voltage divider that can go to space, right? Where you have temperature swings between -40 and 90 degrees. You need to make sure that like this voltage divider on your reset line doesn't reset your satellite every time it orbits the planet. So you start needing to use like 0.1% tolerance values and considering that whole stack up at once. So it turns out when you do that, you can just kind of do every voltage divider. It's like, it might be overkill, but you know it's done.
But the regulator is always the same. You were just looking for different resistors or capacitors, or what everything?
Yeah, that's a good question. So you can change these values. So let's say if we wanted 30 millivolts of ripple instead. So it probably doesn't need to redo the work for the voltage divider, but yeah, we got more output capacitors. Right. So under the hood, this is doing the calculations that are in the datasheet for any buck converter. How do you choose the input capacitance and the output capacitance? How do you choose your output inductor based on the parameters that you feed it?
So what is the regulator here?
This is a little
Can we see schematic?
buck. Yeah, sure. Let me grab something. Get that schematic to show up. Okay, yeah, here's our schematic.
So it was automatically created from the code.
Oh yeah. Oh, I didn't attach it to ground, so it's got ground as a label. So I'll do that next. It gets some better layout hints when it can do ground. But yeah, so here's our voltage divider we've been talking so
I'm
much
curious.
about.
So change the output voltage. I'm curious. I would like to see how the divider will change.
You want like a so these
it's
real
30
parts,
and
right? So it's 30K and a 9.53.
Okay, so change the output voltage to something else.
Sure, yeah. And so just to say, it's also done your entire bill of materials in real time for the entire design. So these are all real parts in your schematic that are all also verified, and we'll show that out. So what output voltage do you want?
1.8.
1.8. So it's probably going to see a lot of resistor calculations just because, like, I don't know. I think picking the values here is can be tough. So it's populating the problem space right now.
Oh, okay. Oh, I see. You choose the regulator. You specified the regulator when you were creating this instance. What is instance, or what is it?
Oh yeah. So instance means like instantiate. Like add this thing called buck, and it's this regulator, which is just again a code model, right? So it's a subcircuit, and the really nice thing is that you can put subcircuits inside of subcircuits. So I've got this parametric buck regulator model, which instantiates the component. This is what a component model looks like, by the way. So this was auto-generated.
The regulator. Okay, these are the pins.
Yeah,
of
that's the regulator. Yeah. So it's just like, what's the pin name? What's the pad mapping? And then on a box symbol, which way do you want it to point? And then it'll auto-generate the box symbol.
Oh, this is how the symbol is created.
Yeah, that's right. You can also like import a symbol if you want to like draw fancy things. But if you just want to make a set of box symbols, it's automatic. There's a check on the voltage input, and we'll show how that works later. And
so basically, when you create when this is creating schematic, it will automatically check like, okay, the input voltage of this this chip is in tolerance with the voltage which is coming in.
Exactly. And actually it knows you can put in your operating temperatures, and it'll run like a full derating analysis on all of your components. So, like a lot of people have this checklist of like, all right, here's 200 checks to run this design. And then they try to give it to a human expert, and you say like, okay, go check. And humans don't work very well that way. It's just not a thing that people really like. This would be
very tiring to check everything.
Yeah. So are we finished up? All right. So it ran. We've got our board here. Get the schematic to show up.
Yes.
All right. And we've got distance values here. Yeah. So 13K and 102. Or no, 10.2.
Yeah. And you can you can adjust the schematic so it looks nicer. You can manually adjust the schematic.
Yeah. I think something that would help is if I attach ground to ground, so it gets the symbols help it give it a lot of hints about which things go where. All right. Get a ground symbol in there. Soon, update the board. Just add a little more each time. All right, I don't need to rename the sheet. I can just go to it. All right, yeah, so we've got ground here. And there's different things you can do to get in and customize it. We are actually doing the next generation of this right now. So it's going to be able to do better layouts more automatically. But yeah, we still have the nice thing of like, you can't make a drawing mistake in your regulator. Yeah, I think drawing things always seems like a little crazy as design
R3, can you
input.
move R3? Yeah,
Which
oh,
one?
R4, sorry. I use Slovak
R4. Yeah,
language.
yeah, yeah. Maybe do like a.
Yeah.
You can flip it, mirror it. Oh, this is the boost compensation.
Oh, yeah.
So probably like things like that, and then this is
Oh.
on the feedback network, I think. Yeah. All right. So this is okay, but we're making this better as well.
And then when you change something in the code, everything what is not related to the change will stay same. Yeah, it will not move.
That's right. Yeah, we call them the stability algorithms. So we do a lot of work to make sure, like, when you've nudged something, like, I know most people are used to, like, their entire design is nudging things, but when you nudge something in JITX, you try not to lose that change ever. So if I added, for example, like another regulator, let's say maybe this one's 5 volts, and I don't need it to be pre-placed. Maybe the ripple's 45 or whatever.
Do you have also different regulator? Can we try different regulator?
Yeah, I think I got some kicking around. Let's see. What do I have? I got a bunch. That's fair. Oh, that's in a. Sorry, I'm in a demo directory here. I don't have access to everything. All right. This looks like a regulator. It's like quite a substantial regulator. Anything for the module? No. So this part might be there might be a lot going on with that one. With code, you can do a small code change and have a lot of things added to your design. All right. Okay, so yeah, it's going to be doing some quite involved switching regulator design for a minute. But I can show you, we talked a little bit about checks.
Okay.
So you're writing all this fancy parametric code, right? You can feed in parameters and it'll calculate your inductors and your capacitors and try to guess the right parts. But if it's not right, it's not useful. So it turns out that in code, you can have a pretty sophisticated and like detailed model for what a part is, what it's for, and how it's operating. So here I've added annotations for like, what is the voltage? And this is, when we run it next, I wonder which, oh, that's a lot of regulator that we added. All right, some work to do there. So here's another regulator. It's got a lot going on with it. I think that's a PMIC for probably like a sock. Yeah. Anyway, let me get rid of that for the time being. So I'm going to rerun that with these voltage annotations added, and then we're going to look at the check report. All right, don't need that. So it ran 83 checks on this regulator. A lot of them are about data integrity. So it's saying, yeah, I have rated temperature data for these things, not for these things. We have that power pin check. So it says, all right, yeah, 20 volts is within this operating range of 3.8 to 30. It has rated temperature checks, which are, your operating point is within, all of your components are rated for the temperature that you're operating. We have resistor checks. So a bit gratuitous, but these are derated reliability checks saying that the power dissipated by your feedback divider is not blowing out the power spec for your resistor. It looks like it's safe by 2 orders of magnitude, but nice to have that surety. And then you also have all the capacitor derating checks as well.
This is much
Yeah.
more complex than what I originally actually thought. I originally thought it's like you write code to create the schematic in PCB, but this is actually much more.
Yeah, I think it's like speed and correctness is what it comes down to. And we built a lot of this just by talking to a lot of electrical engineers and figuring out like, what do you need to actually go faster?
Mm-hmm.
And if you automatically create some design without having the surety of an expert basically reviewing it for you, then that design is not nearly as productive, right? Because then you have to check it yourself, and then your job just becomes checking, and like checking's already the hard part. So we invested a lot in this code model. How do you bake in correctness? Because the nice thing here is that in my design, I just had to say check. I don't know. I don't have to be an expert on how to derate capacitors for reliability, right? And the people on your team don't either, because like I mentioned, you can write libraries that are reusable. You can put checks in those libraries. So like if you write your DDR library, for example, you can like have a little verification report that runs anytime someone uses that code. So when they include it in the design, has it been attached correctly, right? All of this, like for a crystal resonator, there's like this 100-page application note from STMicro, which is like, all right, here's how you get your critical gain and your like all of these different properties about how to get a resonator to actually start resonating. But you can just automate it, right? So it just becomes a check, say like check the resonator.
How
And
difficult it is to learn to write this code?
Yeah. We designed the language for hardware engineers, of which I am one. Like I'm not a software developer, and I could write it. So there's one positive indication. We try to have it so you can get like familiar with it within a week, and like doing your first design the next week.
Is it like is there like help or something?
Oh yeah, yeah. So with our customers, we've got this built-in docs, so you can go see how do I make a fab layer, for example, and open up a reference about, all right, here's how you add things to a fab layer. So we invest a lot in docs. And also typically America's shared Slack channel with most of our customers. They're like, hey, I want to do this. They're like, oh, that's a great idea. Then we can help them do it. And then we can also add that to the reference documentation.
What about libraries?
Yeah, so we ship a big thing called the open source or the open components database, which is a big library of components and these symbol generators. So anywhere you see OCDB, that's like an open source code that we release. And we're also starting to put out a lot more reference designs. So actually all the examples I showed today, they're all open source up on GitHub.
This is cool because this is actually very difficult to do in like standard CAD software. Everyone is creating libraries by themselves, but I think in code, actually, this will not be a problem because the code, it could be a problem because maybe some companies would like to create it very quickly, so they don't set up all the, I don't know, maybe they don't go into so much details or.
I will say that collaboration and versioning features for code, like people have made a lot of really good tools for that already in ways that you've never seen in a CAD tool. This is where software engineers also care a lot about the tooling, and happily they built all of it for us. So there's already like great version checking, like how do you know you're using the same version of the library? How do you make sure you push updates automatically, make sure that everything is correct and consistent? All that's automatic. And when your library is code, you have to have less overall data. So for example, what's a part modeled with a QFN? What about this ambic part is? All right, so this is a generated model. Where's our, okay, imported BGA land pattern, that example.
Okay, so this is a component. So component, it has the pins and it has also layout somewhere specified? Or?
Yeah, so we can, Yeah, this is the example for the this design I had up earlier.
Okay.
So this is a Ambic Apollo something. It's a people use this because it has like really, really efficient megahertz per microamp. So if you want to like scale your compute in like a battery intensive application, this is a popular chip.
Mm-hmm.
The annoying thing is got 5 rows of 0.3 millimeter pitch bumps.
Mm-hmm.
So this is I've got set up as a test case for the auto router.
So this is the one which you mentioned. The reference design is on 8 layers.
That's right.
Because
Yeah,
you can't really fan out from the 5th row without going inside of the PCB.
That's right. So this one's got 4 layers, and I think I can do it. I haven't finished the design, obviously, but there is freedom. So this is using the same stack up as the project called Thingy 91 from Nordic. So it's a 4-layer stack up, 100 micron dielectric on either side, 1 layer of microvias. So that ends up being pretty cheap, and you can get really small vias that way. But yeah, this component model was this is all imported. We tend to import a lot of things. So a processor vendor will put out like a pin list or a bump map or a list of pin capabilities, and maybe it's a spreadsheet, maybe it's a PDF. You can just read that with code and turn it into your data model. So this one is a list of pins, and it's also making a banked symbol for the processor.
Okay, so these are the pins, and then where is the footprint? I'm curious how to specify footprint.
I think footprint was imported, if I was gonna guess. Ambic. Where is that footprint? So land pattern, yeah, just imported here. All right, so yeah, this was just imported code. I think they had a source Altium design, so you can import your components, turn them into code, and this was all just auto-generated.
So these are basically some kind of, you specify the shape and position of the pad.
Yeah, so if you start typing this yourself, something's gone wrong. So either import it or we have like a BGA package generator. So this line of code says, I have a pad named L8, which is this dimension at this pose.
On this layer.
Yeah, on this layer, right. And then this is that pad definition. So it just gives it a shape, apply solder mask and paste.
Okay, okay. And where do you specify the other layers, like silk screen?
That's in the land pattern itself. So pad is just the layer stack. They like to show a lot of mechanics.
Screen. Okay.
Yeah. So there's the outline. Yeah. The reference label.
And 3D model.
The 3D model. Yeah.
Huh. Okay, I've got idea how this works. So let's have a look what you can do inside of this PCB layout tool. How can you route it? I'm curious.
Yeah, so let me get this a bit larger here. So I've been working on just kind of playing with this layout. So this is, if I look at the source code so we know what we're working with, this is a Ambic, where's our Ambic design? Ambic demo. Okay. So I find this is faster than quickly reading a schematic. So this adds the Apollo microcontroller, and it's also, you know how you had parameters for the power regulator? You can do the same thing for anything. So they have all this reference documentation like, all right, if you want to use USB, you got to do this, this, and this, and detach this and add this inductor. So you can do the same thing for like, all right, I don't want USB or Bluetooth, but I do want MIPI, and it'll just generate all the reference circuitry. Some voltage annotations. This is a wireless power charger. We've got a statement to pull some control signals from the microcontroller for wireless power. We've got a octal SPI flash. So again, this is using a require statement. So this supports it in a few different spots. So it says like pull one of the octal SPI interfaces and attach it. This again is a constraint function. So match all of the octal SPI signals within plus or minus 40 picoseconds. It also does the impedance constraint, topology constraint.
But here you only connected the powers, if I understand correctly.
I only had connected the
power.
No, this makes the
these
connection.
rules, they make the connection with the processor.
Yeah, so it makes the connection, so you can choose the pin later. It makes the it adds a skew constraint and it adds an impedance routing structure. Just, there's a way to constrain octal SPI, and you just turn that into a function. The same way you could do that with DDR3.
Okay.
And then we've got a little 6-axis gyroscope, and again, just connect to SPI. And then we've got a little MIPI connector. This looks constrained within 5 picoseconds. So yeah, this MIPI, just clock data, right?
What is inside of the Connect SPI? I'm just curious.
Yeah, so this handles the logic for, can I make this bigger? Go to the definition. All right, well. When you have to decide between SPIs, all right, what's master, what's slave, what are the different connections? So this attaches, if you have a bank of SPI devices on a controller, it just manages the logic between all of those devices. So just the logic for if you want to connect SPI to a bunch of things, how do you systematically hook up, clock, data out, data in, as well as it's also going to pull chip selects for extra devices if you don't assign them.
Okay. So how does it know which pin is which on the processor and which one is on the memory chip? So is it based on the pin name or?
So this one, they had a big spreadsheet of, and Ambic is not a large semiconductor vendor, but they have some really cool chips. So they had a big spreadsheet of the IO mux table. So you can read that and then just generate code from it. And in terms of which pins can be where, it's generating the support statement. So this says, I've got this SWD interface with an optional pin. SWO, don't necessarily need it. And it's available on these pins. So if you end up using this, you'd have a require statement saying attach SWD. There is only one place for this, so it will be on those pins. Other things could also be on those pins. Like SWO, for example. Okay, this could be on any one of these pins. And then you just load your entire pin assignment problem into it using this sort of imported code. So ADCs, UARTs, I2Cs, SPIs.
I see SPI, okay. So basically this is how it knows which of the pins is clock, which one is the MISO, MOSI, and chip cell. Okay. And then you just connect, you just tell, connect the SPI from the processor with the SPI from the memory chip. That's it. Yeah,
that's right. You just say connect SPI. And same thing for MIPI, same thing for octal SPI, same thing for DDR. So you take your entire pin assignment problem and you load it into this solver that you then use the router to figure out. So for these dense designs where I'm all right, can I get rid of 4 layers of board and 2 layers of microvias for this design and make it $100 board instead of a $3,000 board? It's really, really helpful. So I've just been, you talk about breaking rules. A lot of this is a little questionable maybe. But if we go layer by layer, top, not much going on yet. It's mostly caps and fan out crystals. We've got copper 1. I've got the octal SPI interface. And these are, so this is how it does length matching. So remember, it's tracking all of your constraints to make sure that you're within this 40 picosecond window. So if I make this smaller, say I don't have enough room for that, we should see, we got some failures here, saying it couldn't length match. Then copper 3, I've not done yet. That'll be power. Actually, let's do power real quick. So I think this is, zooms on top of my UI. There we go. ED A. So this, I'm going to have the auto router do power as a trace, and then I'll convert it to a pour and clean up some of these rat lines. All right, building a little spanning tree. Where's my source? Yeah, it's not bad. I think I'm going to change it a little bit though. Like that. And all right. So I'm going to turn this into a pour real quick. All right. So that's how you do power routing, by the way. So you use traces to span your topology, and then you can convert them into pores, and they negotiate against each other. So if I made this also a pore, it'll carve out some space. So you can do this makes more sense in like really dense BGAs. But yeah, so that's how you do power. And then bottom layer, we've got our wireless charging circuit, power regulation, that kind of thing. Our differential pairs for MIPI. And these are all happy. So I don't have any messages here, which means like it's looking good. All the skew constraints are met. So yeah, if I was going to finish that off, let's see.
So do you check it also if there is a reference plane for the differential pairs, for example?
Yeah, the code is doing that with the assumption that there is a reference plane. So I showed the code to create the routing structure. The next iteration is going to like make sure that that's a reference plane, as well as be able to route around obstacles in the reference plane. So we were talking a bit about high speed earlier. So for a high speed connector, you have this landing pad and you have to like void underneath it. Like if you have like a DIMM socket, for example, you have to route around that, right? You have to make sure that your reference is not going to be significantly impacted. So that, as well as really solid features for via stitching. If you make something like an RF trace, like a conductor blacked coplanar coupled waveguide, you want to like guarantee that these vias are going to be there, which is much the same problem, right? Where you say like, I made this impedance structure assuming this geometry will be here, and now I'm going to make sure that it is in fact there.
Okay, because even if you can place these on 4 layers maybe, but I think it will be super hard to have the good reference planes for the signals, and because it's going to be broken.
So I think I'm doing okay so far. So here at top I have ground, and that's my reference for
Okay.
OctoSpy. Bottom, there's not really much there yet. So, but I think you're right. Let's see if we can make it work. So here's the gyroscope. So we were over here for our pin assignment, right? Is it those 4
Yes.
pins? All right. 1, 2, 3, 4. And give me a top micro via, shift V. So auto via is helpful. When it's via in pad, it's not a very complicated computation. All right, so then I'll move this in place. Get it over here, looks pretty good. And now to route out, I need to break out to top micro vias again, right? All right, so let me just do that. Via type still the same. And get my signals out here. Oop, missed that one. Okay. And now should be able to route, right? Yeah, okay, so this one wants to go that way, which is a bit awkward. All right, I'm just gonna sketch this in. Say we want that, and then we'll pump it up later. That one. And this one goes, in the middle, of course. That's annoying. Let me snake this in this way. Is that the right topology? 1, 2, 3, There we go. Right.
It's
Not
good
bad.
actually.
Yeah, that's not bad. I think these are routed with minimum trace and space. I would probably bump that up to whatever I can get away with. Yeah, that's better.
You can move the via behind all the 3 tracks.
Which one here?
Yeah, the one which you just selected. Just move it behind the tracks, behind.
Behind the tracks.
Yeah,
Oh,
yeah.
yeah. Okay. All right. I'm glad we're on a video chat. Yeah, that's much better. Yeah, there you go.
Years of experience, you know.
Yeah. Yeah. And there's things you can do if you want things to just line my vias up so nicely. Some people like doing that. But yeah, so that's how the routing tool works for all interfaces. So I think this sort of miniaturized, highly dense design, I think I can actually make it work on 4 layers. My reference planes are they're pretty good. You can't assume global constraints, right? You've got to work locally, but I think it can work.
What about placement? Can this do some kind of decoupling, capacitor placement, or?
Yeah, so that's one of the things that's coming next. So it has some helpful things. So we showed the purple nets list for pin assignment. There's a turquoise one as well. So this is VDD. There's a lot of VDD connections. So in code, you can actually have a notion of a bypass capacitor. So notice that the turquoise net list only goes to that pad. Right. So this is opposed to I don't know, some people draw a schematic very carefully to show which capacitor a pin it goes to which pin. So we have that notion in here. And I think next is, we talk to a lot of users and try to build what they want. I think some placement is probably coming soon. So we got asks for even more automation. Once you see a little automation, you're like, well, I don't want to do placement now. I think where we shot for with the router was most of routing is placement, right? How do you make a router that kind of embraces that and doesn't get in the way of you doing placement with your routing tool and trying to make it so it's easy to tune layouts up, you can move things, optimize things. And now I think it's more automation, so more better search in the router, so you can do kind of larger banks of signals and have it sort of negotiate now that it has all of the timing constraints in it. And then I think a little bit of that is going to be placement as well, saying I have a very clear definition of subcircuits, right? Here's my processor, here's my flash. You should be able to collect those up and say all right, give me a great local layout for this, and then I'm going to drag it into place, and then I want it to adjust a little bit to its surroundings. So I think that kind of layout automation is coming next. If you wanted to script things, it supports all of that. So remember the buck regulator. You can do a placement and then reuse it as much as you want. Turn it on and off. But I think you can push that pretty far. Now that your design's in code, you kind of know what to do with it.
But can you specify the placement also in the code? For example, for the regulator, you know what is the most optimum placement. So you don't want to always start from scratch.
Yeah, that's right. So that's totally something that's very normal to do. So all of this was code placed.
Oh,
and you can turn it off if you wanted to, right? So all that came from code. And
so this is kind of you can also make it parametric placement, right? Based on the code. Okay.
Yeah. So you can also make it parametric. So you notice that these caps, the number scales as you adjust the ripple voltage, and you can script that in too. So it's not just a static thing, but you can actually make it so I've got the sort of parametric structures on my board, and I can I know how to put them down. Dragging them around in the layout tool is not interesting. There's no going to be oh, I found a new optimal layout for this. No, you just reuse it.
Can we go back to the previous design? Is it difficult to show, I don't know, let's say the length matching of the SPI interface? I know we don't have to do length matching for SPI. I just would like to understand how difficult it is.
Well, I mean, for OctoSPI, I think you want to hit a window. So the model here is the same one we use for DDR, which is, let me isolate this layer so we can, and you could, You probably have better ideas about how to route this. We're going to drag a via. So the model here is that you give it a region to work with. Then as you move traces, it will dynamically adjust the skew to meet your constraints, right? So if you don't give it enough room, for example, let's say like, hey, I squiggled as hard as I could while respecting your SI constraints, and I could not make it work. So I need a bit more room. And then that constraint exists for your whole bus. That's what that line of code sets up, is like, all of these signals need to be within plus or minus 40 picoseconds.
Okay, so if you would like to length match SPI interface, what would you need to add into your code?
Oh yeah, so the way that code works, see if I can get, sorry, Zoom interface is in the way. All right, our octal SPI is length matched. So this is the code. It gets a little hairy. I guess it's not that bad, it's like 10 lines. But so this is saying, what's my input and output for the connection of octal SPI? And what is the time range that you want to constrain it over? Okay, then you make the net. So you make the connection. And then you define the topology. So I think in Altium, this might be like an X signal or something. Like,
yeah, I understand.
You can,
from
yeah,
this
you can
pin to
only
this
route.
pin, and then order of the.
Exactly. So in the DDR example, that clock, it hits the chips in a specific order, and it is not possible to route it in a different order. So that constraint is added. It sets up a routing structure. So this is the 50 ohm dimensions. Yeah. Constraints topologies, and then sets a timing difference constraint. So this is saying for all of the SDIO pins between in and out, they're going to be matched to the clock within your specified time.
Okay, so let's specify shorter time in the code.
All right, yeah. So what do you want to bring it down to?
Something what we can see in the demo. I don't know.
All right. So gratuitous length matching in octal SPI. No one's done that before. All right.
No,
right, so
it's only to show how it works. Of course, you
yeah.
don't have to do that. I'm just curious.
Well, that was the thing I found. So I've been reading the available materials online for what signal constraints are necessary for octal SPI, because in some reference designs, you'll say length match the signals, just full stop. Right? They don't tell you like their setup and hold time or how the interface works or how you can check that it's correct. It'll say length match it. It's like, well, okay, I guess I'll do what I can with the margin that I have. All right, so I think we're done there. Oh, yeah, so we got a lot more squiggles here. And it's not doing it. So it's saying, I now have 8 issues, as you might expect, saying, I'm hitting 36 picoseconds of skew, and you wanted to be within 10. So not quite enough room to do this. So then you could get in there. This is some of the automation that we're adding, which is kind of assign pins, route, and nudge these regions so that you can get an overall minimum surface area required for the interface.
Okay. Yeah. This was good demo. I thought we will add this on the other interface.
Oh, on the other one.
Yeah, but
probably could.
I
don't have the code for that right now.
We don't have to do that. Now I understand, because I could see there is this time parameter in the model. That's how you specify it. Okay, I understand.
Yeah.
Okay.
And I bet you could route this a bit better than I did, but this is what it looks like. And this works. This can be a really size efficient way to do length matching, because you can get sort of slight variations to make up time along a route. So we're testing this now I had a DDR demo that I turned out not being able to show because it uses some proprietary data, but then we got the OpenRex design to kind of show the same concept.
Yeah. Okay, what is the different example what we would like to see today?
Yeah, so next up, if you want, we could do, you mentioned you're working on a keyboard design.
Yeah.
So
I'm curious.
you want to do a keyboard? Yeah, all right. Everybody likes keyboard. Oh, and I don't need copper 1. Okay, so everything's low speed and nice here. So lots of people like mechanical keyboards. So what you're looking at, actually that's what I've been typing on. So we made our own keyboards during a hackathon, which is amazing. Like, I could get this assembled in 5 business days for $8 each, which is, yeah, it's pretty good. I see all this stuff online about keyboards, like, oh, this keyboard kit is out of stock and it'll be in stock in 2 months. Is like, I could just make my own supply chain. Keyboards are not that complicated. And there's people that actually automated the design. They made all these tools for keyboards. Have you seen this this online tool before?
I think I did. I don't know if exactly this one, but something really similar.
Yeah. So they ended up making their own like JSON schema to describe a keyboard, and you can load in whatever you want. So you can write it on. You have all these pre-made ones, or you can start with a blank one. So we built an importer for this. So I mentioned like it's super common to import all kinds of stuff. Like, you know, these pins support this interface. I'm going to import my FPGA constraint file or import a bump map and just like generate component data. I built an importer for this JSON because it's fun. Yeah, so let's start with a blank one, and we could make a programmer's keyboard. Let's see. So here, control, and I think control is usually wider, right? They have this width parameter, which is, there it is. I think it's 1.5, 1.25. Yeah, that looks like a control button. And for programmers, we have copy, and we have okay. It's probably easier to just edit the JSON directly. Copy. So yeah, this makes a JSON file, and we can just import that. So I have let me show how that systematic importing works. Got keyboards. Here is our, no, not the regulator. There it is. All right. So the way this design works is I made a PCB module, which is the switch circuit that you want to use. So I just pulled some parts from our database. So we got a big database of parts.
So this is the diode, the switch, and maybe sometimes you have LED there.
Yeah, exactly.
So this is everything associated with one key.
That's right.
One button. Okay.
And then I wrote a function to read in, you know, the JSON format that they write, and I give it what button do you want to use in your keyboard, and that's it. That's enough to generate the entire key matrix. So yeah, let's start a new one. Let's do a new file. We'll make this like AI coder JSON in layouts. Yes. We'll paste in our design. For some reason, that tool doesn't give you valid JSON to copy out, so you have to like make it a valid JSON file. Annoying. There we go. Control C and Control V. That's how I do most of my programming. Don't need a buck regulator, don't need an ambic part, don't need bundles.
So this will be 3 buttons.
Yeah. I think that's my AI coder JSON, and I'll save that as a new file. Let's split that off. Yeah, so the input is a standard JSON. And the thing I really like about this JSON is that someone wrote a firmware generator for it. So you can like automatically set up all of the key mappings and firmware code as well. Let me just do that. I've loaded a lot of active designs today. But if I can get, yeah, there's my active keyboard. All right, Control CV, easy.
Even the
You can get,
placement is correct. I see the control is a little bit wider.
yeah, that's right. And you know, add silkscreen to map out what it is. And you can just keep going. You know, I think this is where it gets really nice. You know, you have your automation set up, and then you're just coding, right? You
Make
get
one
to
of them
sort
wider, like I don't know.
You want a wider one?
Yeah, yeah.
Oh, like yeah, let's get a big C key. Make it easy to hit. I think their format is W for that, so it's width is
3
the
times.
size of a space bar. Control, and then it wants a comma. Ugh. Okay, where's our board? Yep, there's a big, that's a big C key.
You know how much time I spent with placing all the components and related components on the keyboard, which I was designing? A lot of time.
A lot of time. Yeah. It's I mean, hey, if you got a layout, I can make you a JITX design. I can export that to Altium. Have you finished already?
It's finished. Yeah.
All right. Next design then. I think Alt.
So, but this is good to show that if, for example, a company is doing many different modifications of one thing, this is like super fast.
Yeah, exactly. And you find that in design, all right, it doesn't like my JSON for some reason.
Because I'm sure like creating the code takes some time, okay? Creating the support for importing this keyboard takes some time. But once you have it done,
yeah,
all the modifications are super fast.
Yeah, that's right. We try to build automation so that it just makes your code more powerful, right? So, yeah, the other thing it's doing is doing I/O assignment for your microcontroller, right? So you can figure out what I/O pins. Again, little IoT processor here. It's kind of a pain. Like half the I/O are assigned to this inner row that's not accessible unless you get like fancy vias. But yeah, you can use it to rat out. But yeah, anywhere you've got standard data, you know, there's like 100-page PDFs of VPX backplane standards, for example, and all of that. There's like a lot of like really rich domains for automation here, especially like large complex components with a lot of regularity, like an FPGA or a processor, right? Honestly, writing the importer to bring that data in systematically and then creating the design is faster than just drawing it. Just because of the amount of work and rework you have to do to like create the design, improve it, recheck it. You find it crosses that usefulness threshold pretty quickly.
Is there support for 3D models? Because I've seen in code you had 3D models, but I don't see any 3D visualization here.
Oh yeah, that's coming soon. So 3D is in there, but we've got to port. We started with this kind of rendering kernel that we're going to replace with WebGL, and then we'll have better support for 3D. But right now what it does is when you export your design to Altium, for example, all of your 3D models are there as usual.
Okay. So you can export this? But this one doesn't have 3D models. The switches, they don't have 3D models.
I don't know if I added them. I would have to check. Some things that come in from the database have them, some things don't. It would be helpful for a keyboard, huh? But I'm actually not on my Altium computer. This is on my Mac.
Okay.
Yeah. But yeah, we'll get some 3D views out.
Okay, yeah. Is there any other example what we would like to?
Yeah, I think the last one is DDR. So we kind of started with this one.
How we started.
Yeah, so bringing it back, you know, we talked about pin assignment and require statements. I create a code model of this processor that holds like what pins can be assigned to what, as well as how to create all of the topology and timing and length matching constraints, so that at the end of the day, you can get into your router and figure out, okay, for this byte lane, how do I want to route it? Including all the subtleties of like, remember from your video, it said DQ8 only has one option per byte lane because you have to do right leveling. So then, yeah, I don't know, maybe we have a way to share tool control via a web interface. So you'll probably be better at routing this than I am if we had that hooked up. But yeah, I think we come back to how do we very quickly make assignments here. I don't know if I can fit between those balls. Yeah. To be able to just, I think, systematically manage all the really complex information that usually lives outside a CAD tool is what I keep coming back to for the utility of code. How do you bring it all in one place so that you can use optimization to make better designs faster and have like the correctness sort of managed automatically?
Oh, why did you cancel the? Yeah, okay.
Oh, you want me to keep going?
Yeah.
Okay.
Just connect
Let's see.
8 or well, how many?
Let's try to get these 8 in. So here, yeah, I'm using the manual routing mode to say like, I think I'll get these going exactly where I want them. And get this one escaped first. Okay, that one can go there. That seems good. This one, be a good neighbor. I remember this one should probably go further to minimize the overall skew of the group, right? Maybe this one can go there. There's probably a better way to choose this. Yep, so there's a byte lane.
Okay, can you do length matching?
Looks pretty even. I think I would have to do a decent chunk more routing to get length matching working.
Okay.
I could try. But yeah, let me see. Because these are, let me remember, length matched to the clock for DDR. So we'd have to route the clock, which is, I think, terminated here, to know how long they need to be. Yeah. All right. Well, let's try.
They need to be length matched to the SDQ. Clock just needs to be longer. SDS. I'm sorry. SDQS. The differential pair.
Yeah. Yeah. So there's a constraint on DQS within the byte lane, and then there's also constraints on
the clock.
On the clock as well. So right now it's not routed, so it's not going to be like, I don't know how to length match this. Oh, actually, I think I had a team member created this design. I think I had a snapshot. Yeah. Okay. So this is OpenRex.
Yeah.
That looks pretty familiar. Yeah. So I think we were routing this lane down here, and then we had. Oh yeah. So here's the length matching results.
Oh, I see. Okay, so you routed the clock here in this example.
Yeah, so here the clock was routed, just roughly. I'm sure there's better ways to do this, just to test the length matching. And it squiggled the hell out of it. So I think it's, do you remember what the timing constraints between the
I don't know.
DQ
Usually I put there 10 or something.
Okay, I think these are going down to like 3. So it's being
plus
very
minus
thorough.
3.5 picoseconds.
3.5.
Yeah.
So yeah, and that's what it looks like once you get all the length matching in.
Okay. Only my last concern would be like, it's always fun to route first 90%, but to finish last 2%, that's when everything gets really hard.
I agree. That's why I've been kind of driving with the. Where's my Ambic test case here? So I try to just make these punishing layout problems to test the tool of like, all right, this is way too small. It doesn't have enough layers. Can you finish anyway? And it's going okay. I think it's actually a pretty powerful way to create a layout. I do want to add more automation to it though, because a router, like we're mostly doing point-to-point routes here. We pick the pin assignment ourselves, and then later try to solve the length matching problem. But it's all a computational problem now. So now what we're doing is kind of attaching smarter algorithms for search. How do you explore, like, okay, I could route that byte lane, and it's faster than kind of editing the schematic and then editing the layout, but you could just search over that problem, right? So we used like a bunch of AI techniques in our tool just to like get enough solvers to make the coding like a really nice way to do designs. I think we just keep building them, honestly, such that the routing experience just becomes a bit more powerful over time, where you're kind of like, all right, I'm going to search out architectures, because it's pretty good at the last 2% if you can get it in the right shape for optimization. And I think we're there now.
Okay, I've got an idea how this works. I'm really curious where this will go, and yeah, I don't know if I'm going to use it, but it's interesting. I think the code to me it looks like a lot of work to learn initially, so I think that's something what I would be a little bit worried. But I'm sure if someone is designing or doing a lot of similar designs, if there are companies, for example, doing a lot of similar designs, they can use this. And I'm curious where you will go with all the very high-speed designs, which, for example, maybe server boards or something, if there is no space limitation, but I don't know, the timing and routing can take a lot of time because of the, I don't know, manual detailed work. I think that's something also where it could save a lot of time.
Yeah,
Many
sorts
pins,
of structures.
many pins,
lots of pins.
large boards. Yeah,
it's pretty good for little IoT doodads as well. Well, thank you for the feedback. This is how we've built all of this so far. It's just kind of show it to people and use it. It's like, is it working? No, yes.
Actually, I'm quite impressed how nicely it can connect it can make the connections. I think I don't know if I have seen a tool which can do it so quickly and so kind of intelligently, like good way. Nice.
Thanks. Okay. Yeah, that's good, because we just shipped this version of the router on Tuesday and we're recording on Friday. So, and it took us about a year to build it. But now it's in this shape. I think we ship every week. So we've been adding capabilities to this pretty fast. So any feedback you got, we can probably turn into features pretty quickly as
Ship,
well.
it means it means updates, or what
updates.
Okay.
Yeah, so we just update through VS Code, and we have like a weekly release cycle.
So if someone would like to try this, they can just sign up through the website, or they would need to contact you or something?
Yeah, they can sign up through the website, or they could ask for a demo if they wanted to talk through an application. We're in the phase of, let's take on customers that get a lot of value out of this, and then just make sure they like absolutely succeed in unreasonable
So that's
amounts.
why it's probably $1,000 a month, because maybe later you will have also different kind of pricing, but right now you are mostly interested about the companies which can really benefit from this tool, correct?
That's right. Yeah, so like I said, we really live on feedback. So people that really want to use the tool a lot and are going to get in and get a lot of value out of it is where we're targeting now. And then, not everybody needs like a full AI data center auto routing server card tool. So you can probably make it available for cheaper amounts. But that's also why we have the tokens. So if you have like spiky usage and you just need to like get a design done and then you're writing firmware for 4 months, that's what that's meant for.
Okay. Thank you so much, Duncan. I'm curious what people will say about this. So everyone who would like
Yeah,
to say something, leave comments. I'm very curious to read them. I'm pretty sure
me
you would
too.
like to know what people will think.
Absolutely.
And
Yeah.
again, thank you so much for your time and for showing me this. I think it's a different way of doing schematic and PCB layout. So that's why I wanted to create this video.
Yeah. Yeah. And thank you so much for reaching out to ask questions. And thank you for the feedback.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedDevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.